Hi guys, this is Mrs. Allison. Today we are going to look at the second day of L'Hopital's rule, and we're going to focus today on those other 5 indeterminate forms. Now, what I want you to do is I want you to try these 3 limit problems up at the top, keeping in mind you may need to use any limit techniques that we've come across so far in our study of calculus. So why don't you hit pause and come back and check your limits. All right, for this first limit, the limit as x approaches infinity of sine of x. So really, what is this graph doing as we move x towards infinity? Well, it's the sine of x, right? And if we picture graphing the sine of x, so the sine of x is this cyclical curve that just keeps going, right? So as we move closer and closer to infinity, do we ever get to a value for the limit? No, we do not. Therefore, this limit would be does not exist. DNE. All right, what about the next one? I cannot use L'Hopital's on this one either, just because it doesn't fit the pattern. I don't have a 0 over 0 or an infinity over infinity because the limit as x approaches infinity of sine of x, we just said doesn't exist. So it doesn't exist not because it's 0, not because it's infinity. It's not there. There's no limit. Whereas the limit as x approaches infinity of x cubed, there is. Well, there is something called the squeeze theorem that we would have talked about, or you would have talked about when you first started doing limits. And the squeeze theorem says, think about 2 numbers that they're sandwiched between. So think about the sine of x. So if we have the sine of x, we know that that is between -1 and 1. And so if we look at this, and I put x cubed in the denominator here for just a second, and I think about, do you agree that this sine of x over x cubed has to be between -1 over x cubed and 1 over x cubed? Right? Sine of x has to fall between -1 and 1. So therefore, sine of x over x cubed has to fall between, sine of x over x cubed has to fall between -1 over x cubed and 1 over x cubed. So let's think about the limit as x approaches infinity of these two. What is the limit as x approaches infinity of these two? Well, I have -1 over a really, really, really big number, which means 0. And I have 1 over a really, 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 really big number, which means 0. Therefore, by the squeeze theorem, the limit as x approaches infinity of sine of x over x cubed is 0. Great. On to the third one. If we look at the third one, this one we actually can use L'Hopital's, and here's why. Remember, to use L'Hopital's, to be L'Hopital ready, we have to have it equal one of the indeterminate forms of 0 over 0 or infinity over infinity. And if I look at the limit as x approaches 2 of the integral of 2 to x of e to the t dt, this would give me, substituting in, would be the integral of from 2 to 2 of e to the t dt. And if I subtract a value from itself, I'm just going to get 0. So that limit is 0. And if I look at the limit as x approaches 2 of x squared minus 4 on its own, that also is 0. So this is L'Hopital ready. And since it is, what I'm going to do now, I didn't leave myself enough room up here, sorry. What I'm going to do now is I'm going to take the derivative. I'm going to apply L'Hopital's rule. And then I'm going to be doing the limit as x approaches 2 of the derivative of the integral from 2 to x of e to the t dt, which would be e to the x, over 2x, the derivative of x squared minus 4. And therefore, when I make a direct substitution in here, we would get e squared over 4. So the limit in this case would be e squared over 4. All right, how'd you do? Well, may need to revisit some of our limits again, but this is why we are bringing this back in this unit. Now what we're going to do today is work with the other 5 indeterminate forms. So let's review those other 5 indeterminate forms and then look at how we can evaluate each of them. We're going to make them each L'Hopital ready. And it's going to take some algebra work on our part. So our other 5 indeterminate forms. We have 0 times infinity, and this could be either positive or negative infinity. We have infinity minus infinity. We have infinity raised to the 0 power, 0 raised to the 0 power, and 1 raised to the infinity power. So each of these are indeterminate forms, but each of these requires us to do some work to make them L'Hopital ready. Okay, let's begin. The first form that we're going to look at is where we have the limit as x approaches c of f of x g of x, and the limit as x approaches c of f of x is 0, and the limit as x approaches c of g of x is either positive or negative infinity. So we're really looking at the 0 times infinity or the 0 times negative infinity. That's our indeterminate form. Now what we're going to do with this form is we're going to write our f of x times g of x as the product of a fraction rather than the product of two just functions. So we can rewrite f of x times g of x as f of x over 1 over g of x, or we could do g of x over 1 over f of x. If you look at each of these, you could see that if we were to do the division, f of x divided by the fraction 1 over g of x, really we get back to f of x times g of x. Once we get it to this form, we will be able to apply L'Hopital's rule and then simplify. So let's look at a very generic example before we go on to example 1. If I have something that is 0 times infinity, right, which we get when 0 we get when we do 1 over infinity, and infinity is just infinity, okay? Or we may get it if we get 0 times 1 over 0, or a number approaching 0. Both of these are examples of how we can take something that starts out in the 0 times infinity and what it looks like when we rewrite it as a fraction. So if we rewrite it as a fraction, 1 over infinity times infinity gives me that indeterminate form for L'Hopital that makes it L'Hopital ready, or 0 times 1 over 0 gives me L'Hopital's form, makes it L'Hopital ready. So let's look at an example. Let's start with example 1. I'm going to scroll up just a little bit. In example 1, what we have is the limit as x approaches infinity of x times sine of 1 over x. Now, if we were to look at this right now, if we were to make a substitution in as written, so let's do it as written, and I were to do the limit as x approaches infinity of x, we get infinity. And if I were to do the limit as x approaches infinity of sine of 1 over x, sine of 1 over x, we would get 0, because 1 over infinity would be really close to 0 and the sine of 0 is 0. So we have here, what we have here is 0 times infinity. It's in a different order, but that's okay. So what we really have here, is 0 times infinity. Okay, well, I don't want that. That's not L'Hopital ready. So what I'm going to do is I'm going to take and rewrite this. And I'm going to rewrite this the limit as x approaches infinity of sine of x, so that's a sine of 1 over x, over x, but I'm going to write x as a fraction. So I'm going to do it 1 over x. So the sine of x over 1 over x really just gives me the same thing I had. I'm just rewriting it in a slightly different order. Now let's check this. When we check this one with the division, the limit as x approaches infinity of sine of 1 over x, we already said was 0. And the limit as x approaches infinity of 1 over x is also 0. And so therefore this is L'Hopital ready. we can use L'Hopital's. So what I'm going to do now is I'm going to indicate that I'm using L'Hopital's rule, and I'm going to rewrite my limit. So the sine of 1 over x would be cosine of 1 over x times the chain of 1 over x, which would be negative 1 over x squared, over the derivative of 1 over x, which would be negative 1 over x squared. Well, the beauty of this one is then those terms cancel out. So really what I'm finding is I'm finding the limit as x approaches infinity of the cosine of 1 over x. And so therefore that's just the cosine of 0, which is 1. So my limit for as x approaches infinity of x sine of 1 over x is just 1. But I had to make it L'Hopital ready. So I had to rewrite the fraction, rewrite the function as a fraction so that I could apply L'Hopital's rule. Remember, L'Hopital ready means it's 0 over 0 or infinity over infinity. We talked about that yesterday. Well, let's keep going because there's 4 more terms or 4 more different indeterminate forms. Over to Okay, the next indeterminate form we want to look at is if we have a function minus another function where they're both infinity. So we end up with the infinity minus infinity. This is the last one we want to look at, or the next one we want to look at. No, sorry, it's not the last one. So what we're going to do is we're going to rewrite f of x minus g of x as a quotient or a product. We're going to rewrite it as a quotient or a product because then what I'm going to be able to do is apply L'Hopital's rule. Or it is possible that I might be able to apply some other methods, such as factoring or rationalizing the denominator, to get it out of its indeterminate form. Remember, the indeterminate forms I'm really looking for are 0 over 0 or infinity over infinity. So let's look at an example of what this might look like. Let's say I'm evaluating the limit as x approaches pi over 2 of sine of x minus tangent of x. And if I were to look at it as it's written, I know that my limit of the secant of x, did I say sine of x? I think I did. Secant of x is infinity, and the limit of tangent of x is infinity. I know this because if I think about both of the graphs of these, we know the tangent of x, its period goes from negative pi over 2 to positive pi over 2 and has a sketch almost looks cubic in nature, but goes up towards infinity as we approach pi over 2. And same with secant of x. Secant of x has those vertical asymptotes where the cosine graph crossed the x-axis, and it goes towards infinity as well. Okay, well, let's keep going. Since this is that indeterminate form, but I need to rewrite it in either 0 over 0 or infinity over infinity, what I'm going to do is I'm going to write it as a quotient or a product. Okay, so I've got a subtraction here. Both of these are trig ratios that can be rewritten. So let's rewrite this, and I'm going to rewrite this as the limit as x approaches pi over 2 of secant is 1 over cosine of x, and tangent is sine of x over cosine of x. And so if I write this as one quotient or product, I can say that this is equal to the limit as x approaches in pi over 2 of 1 minus sine of x over cosine of x. Okay, so now if I look at evaluate the numerator and the denominator to see if this is L'Hopital ready, the limit as x approaches pi over 2 of 1 minus sine of x, when I substitute pi over 2 into sine of x, I get 1 minus, oh my goodness, pi over 2. 1 minus 1, the sine of pi over 2 is 1, so 1 minus 1 is 0. And the limit as x approaches pi over 2 of cosine of x is 0. So I am now L'Hopital ready. And I'm going to make a note that the process I'm using right now is L'Hopital's. I'm going to indicate that I'm changing this using L'Hopital's. Otherwise, it doesn't really make sense as to why my limit can just change. And yes, that is a good habit to get into for the AP test. So we get negative cosine of x would be the derivative of 1 minus sine of x over negative sine of x for the derivative of cosine of x. And now when I make my substitution in, the limit as x approaches pi over 2 of negative cosine of x is 0 and 1 for sine of x. So this limit would be 0. So we've taken it from the indeterminate form of infinity minus infinity and turned it into something that was L'Hopital ready. Let's look at our last three indeterminate forms. 0 raised to the 0, infinity raised to the 0, or 1 raised to the infinity power. Each of these is going to be solved using logs. And I will also link the explanation as to why we use logs in this case, the backstory and how it's actually built from the both sides. I am going to take a shortcut and I'm just going to show you what we're going to do. Now keep in mind, if I'm changing an equation, if I have an equation, I've got to change both sides of the equation to keep it true, right? Okay, so really, if I'm not changing an equation, what I do to one side or what I do to an expression, I have to also do the inverse of it. I have to undo it from that expression. Otherwise, I've changed the whole problem. And I don't actually want to change my whole problem. I'm just trying to manipulate it to make it look like a form I can use. Okay, so I didn't give you any guidelines because although there are some, they're kind of hard to explain in steps. But what we're going to do is we are going to use logs to undo the powers, and then we'll have to use exponents to redo the powers because logs and exponents undo one another. Now, typically, we're going to use the natural log, so that's what you're going to see me use. Okay, so we are going to change this limit just a little bit. Because we're using logs, I can only evaluate the limit as x approaches 0 from the right because the domain of logs does not allow us to do it from the left. Okay, just watch. So the first thing I'm going to do, I'm going to take the limit as x approaches 0 from the right. And I'm going to write this, instead of x to the x, I'm going to write it as the natural log of x to the x. The natural log of x to the x. Okay, in doing so, what happens is I can rewrite this limit to be the limit as x approaches 0 from the right of x times the natural log of x, using my properties of logs. Now the advantage in doing it this way, so let's look at it this way. If I take the limit as x approaches 0 from the right here, we get 0. And if I take the limit as x approaches 0 from the right of natural log of x, when I do the natural log of x, this here will be negative infinity. And so therefore, I have the indeterminate form of 0 times negative infinity. Now we go to the guidelines we've written before. So if you remember, we're going to now rewrite this in fraction form. We're going to change this to be f of x over 1 over g of x, or g of x over 1 over f of x. So what that looks like is I'm going to rewrite this as the limit as x approaches 0 from the right of the natural log of x over 1 over x. Now, if I look at my top numerator and denominator, my top and my bottom, and I take the limit of each independently, like L'Hopital's tells me to do, the limit as x approaches 0 from the right of the natural log of x is negative infinity. And the limit as x approaches 0 from the right of 1 over x is positive infinity, because 1 over x is that rational function. There's an asymptote there. You guys, this tells me it's L'Hopital ready. So this is L'Hopital ready here. So what I'm going to do now is I'm going to apply L'Hopital's rule and say, okay, this has to be the limit as x approaches 0 from the right of 1 over x, that's the derivative of natural log, over negative 1 over x squared. Well, that's going to allow me to rewrite this as the limit as x approaches 0 from the right of negative x. And if I take the limit as x approaches 0 from the right of negative x, I get 0. Now, you might think this is going to be the answer, but this here is not the answer just yet. The reason this isn't the answer just yet is because we need to undo the natural log that we took. Okay, so we need to undo the natural log that we took. We're going to call that exponentiating. So we don't want to forget I'm going to say don't forget to exponentiate, meaning this actually, when we go to evaluate our limit, would need to be e raised to the whatever power we get here, and that's going to be e to the 0. So my full limit, I'm going to erase this part right here. Oops. My full limit here is e raised to the 0, which is just 1. So the limit as x approaches 0 of x to the x power is 1. Let's try another one just like it. If I take the limit as x approaches infinity of 1 plus 1 over x raised to the x power. If I substitute infinity in and I look at this, what I'm going to get here when I substitute this in, this would be 1 over 0, or sorry, 1 over really big number. So this is essentially 0. So 1 plus 0 to the infinity power really leaves me with 1 to the infinity power. Okay, we know that's an indeterminate form. So then my first step, and I don't need to worry about infinity changing the sides, my first step then is going to be to take the natural log of 1 plus 1 over x raised to the x. The reason we would do this again is because it brings down that variable. It brings down that exponent that's a variable. And so I can rewrite this as the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. Now, if I look at this here, what I'm going to see, the limit as x approaches infinity here with x is just infinity. And the limit as x approaches the natural log of 1 plus 1 over x, I forgot I changed the size of that, 1 plus 1 over x is just 0 because the natural log of 1 is 0. So really I have, infinity times 0, which is that indeterminate form that we can't use just yet. But it is the indeterminate form that we can rewrite by changing this into fraction form. So let's change this. So this would be the limit as x approaches infinity of the natural log of 1 plus 1 over x over 1 over x. So let's check L'Hopital's now. If we do the limit as x approaches infinity of the natural log of 1 plus 1 over x, we again get 0 because that 1 over x goes to 0. And if we do the limit as x approaches infinity of 1 over x, it too goes to 0. So we know this is L'Hopital ready. Now, I'm going to indicate that I'm going to use L'Hopital's rule. I'm just going to scoot this over a little bit. I'm going to indicate I'm going to use L'Hopital's rule. And I'm going to take the derivative. So I would have 1 over 1 plus 1 over x times, well, the derivative of that chain is going to be negative 1 over x squared. And so is the derivative of 1 over x going to be negative 1 over x squared. Then these two expressions go away. Oops, I lost my limit. Limit as x approaches infinity. Now, this becomes the limit as x approaches infinity of 1 over 1 plus 1 over x, which if we plug in infinity now, this term goes to 0 right here. That becomes 0, so I have the limit, so I have 1 over 1. Plugging in infinity, I get 1 over 1. So this is 1. Now, just as before, I need to take this 1 value, and I need to take it and plug it back into the undoing of the natural log that we started with. So I have e raised to the, this time it's going to be to the first, because that's the value I just found. And e to the first is just e, so my limit as x approaches infinity of 1 plus 1 over x to the x power is e. Actually, that's how we derive e from the very beginning. That's how e was found. As x moved closer and closer to infinity, we noticed it equaled that same number, and that's where the value came from. That's where Euler named it from. But that is using L'Hopital's rule. So those are our 5 indeterminate forms that require a bit more work on our part. So what I want you to do now is try a fun one. How many of you have seen the movie Mean Girls? Well, if you haven't, you'll remember in Mean Girls, Lindsay Lohan, whose character's name is Katie, ends up going to a math competition. And in this intense moment, she gets this limit problem, and she is able to answer the limit problem. So what I want you to do is hit pause and see if you can answer this limit problem. The limit as x goes to 0 of the natural log of 1 minus x minus sine of x all over 1 minus cosine squared x. So hit pause and come back and try it. All right, how'd we do? Okay, let's try it. So first thing we should check is, can we plug 0 in? And what we see when we plug 0 in is that the limit as x approaches 0 of the natural log of 1 minus x minus sine of x is 0. That's because natural log of 1 is 0. Sine of 0 is also 0, so therefore we have 0 minus 0, which is 0. And if we plug in the limit as x approaches 0 of 1 minus cosine squared x, we get 1 minus 1, which is 0. So you guys, this is L'Hopital ready now. So let's go ahead and use L'Hopital's. The limit as x approaches 0. This is going to be a bit messy, so we get 1 over 1 minus x times by negative 1 for that chain, minus the cosine of x over, we'll have a chain here, so minus 2 cos x sine x. If we substitute in 0 now, we're going to get negative 1 minus 1, and then over 0, so we get negative 2 over 0, and that does not exist. So if you remember in the movie, she said the limit does not exist, and that's her final answer in this. Won't ruin the movie, I guess, but anyway, just thought that was kind of fun because it uses L'Hopital's rule. So now we have wrapped up the idea of L'Hopital's rule. Tomorrow we are going to look at one more topic dealing with limits, and that is relative growth rate and how we can use that in dealing with limits as well. And we will see you soon. Have a good day.